I am Lucia and I will be introducing our low carbon emission aircraft project. The aviation industry accounts for a very large percentage of the greenhouse emissions, and as climate change becomes a growing issue in the 21st century, cleaner methods of transportation must be developed. For this reason, this project focuses on exploring options for low-carbon propulsion systems and identifying and analyzing the most viable one. Particularly, the study's main objective is to prove that hydrogen fuel cell-powered short-haul aircrafts are commercially viable.
For this project, we examined a few different options for reducing carbon emissions. The first was the use of biofuels, such as those derived from methane. Multiple airliners and companies have pledged to use biofuel blends exclusively within the next decade, such as Boeing and Qantas. Another area we looked at is electric flight. This sector has seen a lot of recent development, and research into these systems have been pushed heavily. We also looked at hydrogen power plants, of which not many have been developed, but they have the greatest potential for reducing or even entirely eliminating carbon emissions. And finally, we looked at ways of reducing the use of the current power plants through improved airport infrastructure. Since this did not improve the actual power plant, though, we decided not to pursue it further. Now on to Kastub for our next section.
The focus of this project was building a low-carbon propulsion system for a short-haul flight. And we focused on the shorter flight range, primarily because it's currently a gap within the industry, but it's also an area where innovation can really occur. So while taking a look at this, we started with the propulsion system and iteratively worked backwards to design our aircraft and its system. And with this, we looked into how it could integrate into existing airports and systems, but also we took a look at the different limitations and assumptions we had to make. Obviously, with the scale of this project, our scope is limited to the fact that this is just a preliminary design review, and so we weren't looking exactly into the manufacturing and testing and prototyping of this aircraft.
Takeoff and climb are the most fuel-intensive portions of an airplane's flight profile. As such, replacing the aircraft that perform these the most will have the greatest benefit. Consequently, the team decided to design a short-haul propeller-driven aircraft. The Bombardier Q400-8 is one of the most popular aircraft in this category. Using it as a benchmark, a cruise speed of 560 kilometers an hour and a maximum takeoff weight of 29,574 kilograms were set as target values. Given a 2-hour targeted flight time, the developed airplane needed a 1,120 kilometer range. State-of-the-art zinc air batteries have an energy density of 200 watt-hours per kilogram. Over 46,000 kilograms of batteries are needed to achieve this, making this an impossible aircraft. Hydrogen, on the other hand, only required 2,900 kilograms of fuel, since it has an energy density of 3,000 watt-hours per kilogram. This is reasonable given that a Dash 8 can take off with up to 3,250 kilograms of fuel. However, Jet A has a density of 800 kilograms per meter cubed, so all of that fuel takes up a bit over 4 cubic meters. Liquid hydrogen has a density of 75 kilograms per meter cubed, so those 3,000 kilograms of hydrogen require almost 40 cubic meters of room.
When considering the adoption of any of the alternative energy sources explored above, not only must the pros and cons of its usage for propulsion be considered, but also the infrastructure required to support its implementation. In fact, the infrastructure required to implement many of these sustainable options is the largest barrier to their adoption. Sustainable aviation fuels would require some infrastructure investment, but could also take advantage of much of the current infrastructure for jet fuel, as it acts the same as jet fuel. The main infrastructure issues are the blending of it and the production of it. However, as mentioned before, biofuels are a limited option that does not truly solve the issues inherent to using combustion engines with fuel. Electric aviation poses a much larger challenge to the current infrastructure. Currently, airplanes derive most of their electric power they use from their main engines and their auxiliary power unit. This means that there is very little infrastructure for charging airplanes. Currently, the electric grids at airports are not built to support charging and would require large infrastructure investments. For example, it is predicted electrical usage at O'Hare International Airport with hybrid aircraft would result in a peak demand around 187 megawatts, nearly quadruple the current daily average. Finally, hydrogen fuel cells would require large investments in infrastructure, but also offer extremely large upsides. For the use of hydrogen fuel cells in airplanes to be more efficient than it is currently, clean hydrogen is integral. Currently, there are two main methods of producing hydrogen: steam reforming and electrolysis. The main emissions from steam reforming occur from the byproducts from converting methane, which include carbon dioxide and carbon monoxide. On the other hand, the main emissions from electrolysis occur from the method used to produce electricity. Thus, ideally, it would be possible to produce hydrogen on-site using renewable energy sources such as solar. Airports have great potential for solar power production as they usually have large amounts of land and are located in areas with good weather. Since 7 acres of land have the potential to have 1 megawatt of fixed solar panels, it would be possible to locate 116,704 megawatts on the idle land at airports. There is also a precedent for this. Using just solar panels at the entrances, Indianapolis Airport has hosted a 12.5 megawatt system since 2013. From the equation for electrolysis, considerable amounts of water are required too. In fact, to fully load the 2,918.35 kilograms of hydrogen for the proposed aircraft, there needs to be a source of 729.5875 kilograms of water. Thus, an additional cost to electrolysis would be setting up a water system capable of supplying enough water. Despite the large amount of infrastructure required to produce clean hydrogen, it would sharply decrease emissions in a way other sources cannot compare to.
We concluded that even though biofuels are compatible with existing fueling infrastructure, electrical batteries-based systems have the potential for a greater advancement. However, limitations regarding the integration into the existing system and the current battery technology need to be accounted for. Hydrogen was then also considered, and it was found that hydrogen fuel cell technology eliminates emissions. The main limitation of this approach is the need for a large storing volume. However, this issue seems to be easier to overcome than the mass of a battery. For these reasons, a hydrogen fuel cell propeller aircraft for short-haul flights is the best possible frontier for reducing the emissions.